7. I'm Mrs. Campbell, and today we're going to be talking about classifying polygons. Let's get started. Okay, so we've talked about polygons in the past, but we're going to dig a little bit deeper today. Let's take a look at the definition again. What is a polygon? A polygon is a simple closed figure formed by 3 or more segments. Triangles and quadrilaterals are polygons, and you can see that all 3 of these figures are created by 3 or more line segments. I also think it's a good idea for us to take a look at some figures that are not polygons, just to help us out so we can classify them and identify them more easily. So the first 2 figures, this one and this one, those are not polygons simply because they have curves. Polygons do not have curves. The third figure is not closed. See how it's open there? So that can't be a polygon because polygons are always closed. And the fourth figure has sides that overlap right here. Polygons do not have sides that overlap. So hopefully that'll help you out a little bit. Okay, we've looked at some of these polygons before, but let's do another quick review. Some of the types of polygons that you'll be using and working with: triangle, 3 sides; quadrilateral, 4 sides; pentagon, 5 sides; hexagon, 6 sides; heptagon, 7 sides; an octagon has 8, nonagon has 9, and a decagon has 10 sides. It's a lot. I also wanted to take a minute to talk about regular versus irregular polygons. So a regular polygon is a polygon where all of the side lengths are equal and all of the angle measures are equal. An equilateral polygon, that means that the side lengths are congruent. And if the polygon has equiangular, that means that's the word we use when all the angles are congruent. So here's an example of a regular polygon. It is equilateral and equiangular. Right here, this triangle. And that would be a regular polygon, and this would be an irregular polygon. There's no congruence there. Okay. So now I want to talk about something now that we're going to be using a lot of really big words, but I love learning words, and I think it's going to be so helpful for you to understand the meanings of these words. When you deal with geometry, it just saves so much time. So be sure that you brush up on all your vocabulary. But even though this sounds like a title that's really confusing and scary, it's actually not scary at all. It's actually really cool. Let's try this. So, did you know that we can divide polygons into triangles using diagonals? I'm thinking maybe you read the title, Relate Sides of Polygons to the Number of Diagonals from a Vertex. Don't panic, it's actually easy. Okay, so what this sentence is saying basically is that we can take a polygon, a shape like a triangle or a quadrilateral, we can divide it into triangles using diagonals. And this helps us when we're trying to figure out the sum of the interior angles of a polygon other than a triangle or a quadrilateral, which is really easy to remember. Because it would be hard for you to remember what all the interior angles of a decagon should measure. But there's a quick way that you can be able to figure it out. So let me show you. Look at this little sentence. It says, look at the second sentence. This is important because you can divide a quadrilateral into 2 triangles using diagonals. And each triangle is 180 degrees. That's what this one tells us. Quadrilateral is 360. The interior angles, like I said, of a quadrilateral should total 360 degrees. So let's take a look at an example. Here is one diagonal in the quadrilateral. A diagonal is a line segment in a polygon that joins 2 non-consecutive vertices. A consecutive vertex is one that's next to the other one. So a non-consecutive vertex is a vertex that is not close to another one. And this is where the fun starts. So we've just basically taken that polygon and cut it in half. Now let's look at this hexagon. So here's our hexagon. And you can see what I've done is I have divided it up into triangles. It says right here, this hexagon has been divided into triangles by hexagons. There are 4 triangles. 1, 2, 3, 4. Okay. If the sum of the interior angles of each triangle is 180 degrees, remember we told you, every triangle has to have a sum of their interior angles has to be a total of 180 degrees. So all we basically have to do is multiply that times 4 because we know we have 4 triangles. And then we will find out what the sum of the interior angles of a hexagon will be. Let's look at it just as a simple multiplication problem. 4, the number of triangles we made, times 180, the number of degrees per triangle, equals 720 degrees. See, it looks scary, but it wasn't that bad. All right, one more quick question though. What if we don't have a picture of the polygon? Then what do we do? Well, this table shows us the number of triangles related to the number of sides in a polygon. So let's take a look. If a quadrilateral has 4 sides, it will have 2 triangles that we could make inside of it. If a pentagon has 5 sides, 3 triangles. Hexagon 6, number of triangles 4. Are you picking up on a pattern here? I hope so. Heptagon 7 sides, 5 triangles. So the pattern is that the number of triangles is always 2 less than the number of the sides of the polygon. Okay, so we can actually write that as a formula, and that way we can always be able to figure out the sum of the interior angles of those shapes as long as we know the number of sides they have. We just have to take away 2 and times it by 180. So here's how we write it as a formula. If we want to assume that x equals the number of sides, x minus 2, so the number of sides minus 2 to get the number of triangles, times 180 equals the sum of the interior angles. So let's give this a shot. Let's see if it actually really works. What is the sum of the interior angles of a decagon? Okay, a decagon has 10 sides. Dec means 10. So that's going to be our x measurement. So x minus 2 times 180, that's the number of degrees in each one of those triangles. Okay, 10 minus 2 for the decagon times 180. So 10 minus 2 is 8, that's pretty simple. Multiply that by 180 and we get 1,440 degrees in a decagon. So that way you don't have to walk around and commit to memory the number of degrees in the interior angles of a decagon. You can just do this simple formula to work it out. All right, everyone, I hope you had a great time. Thanks so much for joining us. We'll see you next time. Bye-bye.